Hello everyone. So today we will start module 9, that is on liquefaction, and this is the 31st lecture of remote sensing for natural hazard studies. So let us try to understand what is liquefaction, and then we will go ahead with the studies related to the liquefaction. Before we start digging into deep, so we will try to understand what is liquefaction. So here you can see the liquefaction is a phenomena observed in soil due to earthquake loadings. So because of the earthquake events, because of the seismic activities, this soil, it loses its strength temporarily or maybe permanently, right? Because of that, this kind of event occurs. So basically it is because of the earthquake and the seismic activities. So earthquakes are primarily caused by the movement of tectonic plates. I hope you all must be aware of it, and you also know that Earth's lithosphere is divided into 7 continental sized plates. So first one is African plate, then we have South American plate, Antarctic plate, Australia India plate, Eurasian plate, Pacific plate and North American plate. So here it is given. So this is from USGS and it was given in 2015. When we see these tectonic plates, so basically these pieces of Earth's top layer which are carrying the continents and oceans are called tectonic plates. So basically here you can see this particular video. So it is carrying the load, right? It may be your ocean, it may be your continent, right? And these plates are not anchored in place but slide over a hot and bendable layer of mantle. So here you can see this is not anchored, right? So it is continuously moving. So this is subduction zone. So here you can see this plate is going inside this and then it is reaching to the mantle, right? And this particular plate is moving in this direction. The tectonic plates are always slowly moving, but they get stuck at their edges due to friction. So what happens during this movement, you can see this is getting stuck for a moment, and because of that what will happen? There will be generation of stresses, and earthquakes are resultant of those stresses. So when the stress on the edge overcomes the friction, there is an earthquake that releases earth energy in waves that travel through the earth's crust and cause the shaking that we feel, and we call it earthquake, right? So basically this is the temporarily stucking of these plates with each other, and during that particular time stresses will be generated, and once they again slip, then those energies will be released, and that is seismic waves, right? So here you can see this particular map, right? So here all the continents, these shapes you can see, right? So do you think that these were like this from the beginning of the earth? It is not possible, right? Because we have talked about the tectonic plates and its movement. So definitely this is also moving. So what you do is take a world map, cut out all the separated land masses, try to join them together and make one large land mass, right? And that will be like this. So this was the beginning of the earth, right? So here this was Pangea, and then all the land masses were together, and then it is surrounded by the ocean. But subsequently over the time what is happening, because of the continental drift, because of the plate tectonics, these land masses are getting separated from each other, and also some are colliding with each other. So here you can see this is the collision part, right, with the Eurasian plate. This is one very nice video which explains how the continents are moving. So this is known as the continental drift. So the map view of India's northward movement towards the Eurasian plate through time. So, you can see how it is moving and it is colliding. So, this is the Eurasian plate, and because of this collision we have the Himalayas. So, this is the Himalayan region, right. So, because of this collision we are having the Himalayas in the northeastern part of India. According to the continental drift theory and plate tectonics theory, the plates are in constant motion. Because of this motion between the plates, stresses are built up, and the release of these stresses generates seismic waves. This is what we discussed in the previous slide also. So, because of that you can see around 250 million years ago, this was the condition of earth where all the land masses were together, and then this is the present day, and subsequently it will be taking the form of this, which we will call Novo-Pangea. Then next 250 million years later after this Novo-Pangea. So, here, and then you will have this after again 250 million years, then that is Pangea Proxima. So, this particular work, the link is given here. This nicely explains the continental drift and the future movement of our continents, right. So, as we learned that because of the earthquake or earthquake loadings, this liquefaction occur, right. As we have seen in the previous slides, the earthquake loadings cause the liquefaction. So, let us understand what are these seismic waves, how they interact with the surface. So, when we talk about the earthquake waves, there are two major categories. The first one is the surface wave, and then we have body waves, right. And the body waves had two different types. The first one is P wave, then we have S wave. When we talk about the surface wave, it is Rayleigh wave and the Love wave. So, these four different types of wave, they are generated during a earthquake event. Now, let us try to understand each of them separately, so that you will understand what is their impact and how they propagate, at what velocity they move, and that will give you more clarity about the earthquake loadings on the soil or maybe the surface. When we talk about this body wave, so body waves travel through both solid and liquid. So, remember this, P and S wave both travels through solid and liquid, and the P and S waves are the two kinds of body waves. When we talk about this P wave, which is one of the body wave, so here it is also known as primary waves, are the fastest in terms of wave speed and are longitudinal in nature. So, you can see here how they propagate, right, through a medium, how they are propagating. It can travel through all mediums because this is a body wave, and the velocity is 5 to 8 kilometer in earth crust and greater than or more than 8 kilometer per second in mantle. So, you can see this is very fast in liquid or semi-liquid, whereas in earth crust it has 5 to 8 kilometer per second. Then comes the second body wave, that is S wave, also known as secondary wave or shear wave, are transverse in nature, right. So, this is how it propagate. You see, it cannot travel through a liquid medium. So, it is only propagating through a solid. So, earth crust is the only target. Velocity is 3 to 4 kilometer per second in earth crust and more than 4.5 kilometer per second in mantle, right. So, this is how the S wave travels. Then comes the surface wave. So, these waves travel through the earth surface and result from the interaction of body waves with the surface of the earth. Now, remember the body waves, those were generated because of the earthquake events, right. And now this surface waves, these are the resultant of the interaction of body waves with the surface waves, right. Rayleigh wave and Love wave are the two kinds of surface waves. So, here you can see how the Love wave and Rayleigh wave they propagate, right. So, here you can see this is the direction, right, and here this is in this direction, right. So, Lord Rayleigh, he was the first one in 1855 who predicted the Rayleigh wave, and this is how Rayleigh wave propagate, right. Rayleigh waves have particle motion similar to a stone throwing in a pond. Velocity is 50 to 300 meter per second on ground surface, right. So, here you can see if I keep a target here, how it will be shaking. Love wave was invented by Augustus Edward Howe Love in 1911. Love wave have vertical particle motion and are generated by large earthquakes. So, this is the vertical particle motion. Here you can see how it is propagating, and it is also known as Q wave. So, sometimes the Love wave are also referred as Q waves in books or maybe in the journal papers. And now let us understand the liquefaction. What is the history of liquefaction? So, liquefaction, as we have understood that liquefaction is the phenomena which is happening on the surface of the earth, right. So, liquefaction has been one of the most studied phenomena in geotechnical earthquake engineering, and engineers have started studying liquefaction after the Good Friday earthquake in Alaska in 1964, and that particular earthquake was with the magnitude of 9.1. Now, you can just imagine how devastating it could be when we have this 9.1 magnitude earthquake, right. 3 months later, the Niigata earthquake in 1964, and here the surface magnitude was 9.5, and it produced the same effect, because the earlier one, if you remember, it is 9.1, here it is 9.5. So, almost similar impact they both had. Both earthquakes produced liquefaction features which started the study on this phenomena around 60 years ago. So, here you can see some of the real images, and the building tilted due to 1964 Niigata earthquake, and this is from this particular paper, right. So, theory of liquefaction, it says seismic waves cause cyclic loading, which is cyclic loading is basically the repeatedly stressed or strained and cause the soil to undergo liquefaction. So, we will try to understand what we mean by liquefaction, right. So, in general, liquefaction is a phenomena in which soil loses its shear strength, and the reason behind the soil losing its shear strength is the excess pore pressure generation. Now, just try to understand this concept. When you are having a cup of dry soil, right, and try to just pour it here. So, what will happen? If it is dry, it will spread. You add some amount of water here, then it will be saturated, not oversaturated, little bit saturated, right, maybe 10%, 20% moisture you can add here. So, what will happen? This will try to hold the particles together because they will have the cohesion, right, and because of that this whole column will stand. Now, you try to put more water here, right, 30, 40, 50, 60, 70, 80%, and then try to pour it here again. Then what will happen? Immediately it will flow, because this is a cohesionless soil, right. So, because of this, the soil loses its shear strength is the excess pore pressure generation. Once the soil completely loses its shear strength, it behaves like a viscous fluid. If you remember, we also talked about the shear stress and shear strength in the landslides, right, and there we also try to understand what will happen if there is a reduction in the shear strength and increase in the shear stress, right. So, here also we are talking about the shear strength of the soil. Once the soil loses its shear strength, what will happen? It will behave like a viscous fluid. I gave you the example of 1 cup of soil or sand with more water, right, saturated one. Then you try to pour it out and then it will start flowing. So, that will start behaving like a viscous fluid. It is unable to bear any kind of loading, because what happens, let us assume a condition where there is a soil column which is oversaturated, right, and it is behaving like a fluid because it does not have any shear strength, and you have a building on top of it. So, what will happen? This will sink or this will get tilted, right, because this particular column is not able to support this foundation, right. So, in such situation we observe this liquefaction. So, it is unable to bear any kind of loading when there is a reduction or the soil loses its shear strength. This causes any structure on it to fail. Fail means either it will sink or either it will get tilted. Liquefaction is observed in loose granular deposits with high groundwater table, because we are talking about the soil, right, and it is getting saturated. So, from bottom we have the groundwater, right, and from top you have this loading. So, when this groundwater reaches to this column, this will start reducing its shear strength, and then this particular column will fail, right. So, here this is the condition when you have soil particle and pore water, and groundwater surface subsidence when you have earthquake event, and then this is getting settled, right, because here the pore spaces you can see, here it is more, here it is less. So, this is before earthquake, this is after earthquake. This is a very nice video which explains the liquefaction phenomena. So, here you can see this particular building, and here you have this layer, right. So, look below the surface, here you have loose granular sediments, right, this one. Now, loose granular sediment saturated by groundwater. So, groundwater has reached to this, then you have earthquake event, and because of that you are having the failure of this soil. So, what happened? This building got tilted. So, why this happened? Earthquake waves caused water pressure to increase in the sediment, sand grain lose contact with each other, leading to loss of sediment strength and liquid like behavior, and this is what we are calling liquefaction. This is the photograph from earthquake San Francisco 1906. Area is underlain by marsh deposit that were covered by artificial fill in the 1800s, and this is from the USGS, right. So, this is a very nice video which explains the theory of liquefaction, right. So, for soil to bear any load, shear strength is one of the most important factor, otherwise how it will bear the load which is on top of this particular surface, right. Shear strength gives us the idea of the capacity of the soil against shear failure. That means, if you know about the shear strength, you can understand what is the capacity of the soil against the shear failure, or under certain circumstances whether this particular building will sustain, whether this soil column will support the structure or not, right. To compute shear strength, engineering properties of the soil is needed. Now, the shear strength we can calculate, and because of that we need to analyze our soil sample and we need to derive the engineering properties of the soil. So, liquefaction occurs in cohesionless soil only, because we are talking about the saturated soil, right, where we are having no cohesion. So, here when we try to calculate static shear strength, right. So, we need effective stress, it is here, which is multiplied with the tan of internal friction angle, right. So, that is needed here. So, once we have these two values, effective stress and the internal friction angle, we can calculate the static shear strength of the soil. And here cohesion is not considered because we are talking about the cohesionless soil, right. Otherwise, this liquefaction will not occur. For effective stress, the unit weight of the soil is required as well as the groundwater table depth. Now, here you can see this effective stress. To calculate it, we need the saturated unit weight of the soil, right, and the unit weight of the water, which is here, and H is the height of the soil column. So, here if the building is here and this is the soil column, then maybe rocks will start, right. So, what is this height? This is H. So, due to shaking, the depth of the soil column increases. So, due to shaking, when there is a earthquake event, what will happen? The soil column H, this will increase. The increase in the unit weight of water, which is multiplied with depth of the soil column, and together it is known as excess pore pressure generation, right. This is what we have started discussing. So, now we have come to this excess pore pressure generation, and the effective stress that we have calculated in the previous slide, that becomes 0 when significant excess pore pressure is generated. So, this is 0 and this is when soil loses its shear strength. So, now we have come to a conclusion when the effective stress is 0, right. This soil is going to fail because there is no shear strength. Let us try to understand the liquefaction again with different perspective. So, stress transfers from intergranular friction to pore pressure, that is the first step. Then when the transfer is complete, the soil loses its full strength. Then partial strength is lost when the transfer is partial. In case of an earthquake, there is a condition of load reversal, because what happens when there is a soil column, let us say this is the soil column, this is the H, right. So, during the earthquake event, and let us say this is water table. During the earthquake, because of this interaction, this particular soil loses its shear strength, and because of that this building is getting tilted. But whether this shear strength failure is permanent or it is temporarily, that depends upon the behavior of this particular soil. So, during the earthquake what happens, because of the seismic activities, right. So, these waves triggers this interaction and then the soil loses its shear strength. But after the earthquake, this soil may regain its original shear strength and then this will be as it was before, but this building gets tilted. This is one of the example, right. So, there is a condition of load reversal. Hence, there is a momentary transfer of stress. So, what is happening? This stress will get transferred. When the load reversal occur, the soil may attain its original strength. This happens only if the sand behavior is satisfactory. So, again we need to look into the engineering properties of the soil or this sand in this case. During the load reversal, if the excess pore pressure generated has the scope of dissipating, it will dissipate and the sand will become comparatively densely packed. So, this is after the load reversal. So, again it is getting densely packed. But if the soil column is confined, there is no space for dissipation of the pore pressure. Suppose if this is one column, this is another column and this is the soil column, right, and this is confined. So, in this case the stress is not getting transferred, right. So, this pore pressure will be confined to this particular column. In that case, the loosely packed sand will not take denser packing, right. So, this will not be densely packed after the load reversal. In such cases, a complete transfer of the stress happens to pore pressure. So, here what is happening? The transfer of stress happens to pore pressure, right. Subsequently, liquefaction occurs. So, this is the flow of liquefaction to understand the phenomena. I hope it is very clear to you. Now, let us talk about the different types of liquefaction. So, the first one is the flow liquefaction and the second one is the cyclic mobility. So, let us understand both of them separately and let us see how they are different from each other. So, when we talk about the flow liquefaction, so here when shear strength is less than shear stress. When we talk about the cyclic mobility, when shear strength is more than shear stress. Now, it is less occurrent, it is more occurrent, right. Very severe, it is less severe. So, this cyclic mobility is less severe than the flow liquefaction. So, both of them are the different types of liquefaction. So, with this I will end the first part of this liquefaction and we will continue this lecture in the second part. Thank you.